Welcome back to the fine-tuning large language models code walkthrough. In previous video, we walked through the generating of synthetic data, and I provided a function for that. Today, what we're going to continue going through is the fine-tuning method. Okay, so let's start loading up our device map. And what I'm doing here, what I'm doing here is determining whether it's a CPU or GPU, and I'm on a single GPU system, logged in remotely. So I know what's going to come back there. Let's load our data set. So earlier in the previous video, I saved off the training, eval, and test data sets. So we're gonna load them there. And this method here, the splitting, is a function I created to just quickly do some splitting of data. And what this does, this method here ensures split. What it does is ensure that the provided data set is a single split and not a data dictionary object. This is useful when loading data set with the load data set. Sometimes I get a data dictionary with multiple splits. This helper function is abstracts away from that complexity, and that ensures that I am always working with a plain data set, usually the train portion, regardless of what gets loaded. Okay, all right, so let's clean this up. And it just returns the data set there. All right, so now that we have our data set loaded, let's get into doing some tokenization. So we're going to use Hugging Face's tokenization, a class. So let's talk about tokenization real quick. What is tokenization and how it works? So tokenization, from both a data preparation and computational efficiency perspective, broken down technically and practically, it is the process of converting raw strings. So if you have a string of letters or words, broken them down into basic units that the large language model can process. For example, you may have a word hello. Well, if you tokenize it, you'll get H is one token, E is one, L is one, etc. Hello world, that can be broken down as word-based tokenization would be hello world. You have subword base, byte level, so the different tokenization types. To give an example of what that looks like, I have this Jupyter notebook, right, where I just wrote quickly some code that takes, and I won't rerun it, won't consume too much time here, but did some installation, and this is running on a Mac M3 with AMD 64, so no GPU, and install my libraries and check I'm using a silicon GPU via MPS, and I load my tokenizer, just using auto tokenizer from Hugging Face, and I gave it this sentence here, and what it does, it tokenizes it down into words, and that's pretty much what tokenizer does. Give it a list of sentences here, and I just loop through and tokenize each of them. Now, for it to work beyond this point, the LLM can't use words, so it has to assign each a numerical value, and then now what that produces is a vector of numerical values. So now you're getting into the vector space. Beyond this, we have, after tokenization, embeddings, and let's just go down to, okay, so next step is where this vector is passed into that for embeddings. So embeddings are dense vector representation of the data, like word sentences or even images, in a continuous vector space, and that's where some of this data now is stored in a vector database, and they're used to numerically represent the text so the neural network can process it. And that's where the mathematical computation happens using these vectors. All right, so for example, let's say you have you're embedding cat and dog. Cat may be assigned a vector 0.14, negative, comma, 0. Negative 0.22, etc. Dog, a vector consisting of like 0.13, etc. And when you do the calculation of these vectors with using a formula with these vectors, the two would be close in the vector space, and this means they're similar things, not exactly the same. So the vectors will be different, the values will be different. So it all boils down to getting it into numbers, into a format that then the neural network can use. Types of embedding: static, one vector per word, context with that context independent. Another type, contextual, vector depends on word and its context. Sentence embedding encodes full sentences or documents. So that's just a high example of what the tokenization and embedding is. All right, so we're tokenizing here, and we're using, let's just give you a quick explanation. This is the model, and use fast. What we're doing here is this specifies to use the fast tokenized implementation, which is backed by tokenizer library. So fast tokenizers are usually faster and can run richer information. So it's just all right, next we'll have, okay, tokenize, and let's add some padding. Okay, I'll explain what this all means. All right, so this pad token here is, this is the token used to pad sequences to the same length, common when batching inputs. So some models like Llama, Llama does not come with, or models like those does not come with predefined pad tokens because they weren't trained with padding. Example, they used casual attention, and attention, that is part of the architecture of LLMs. It's just, it means something more than, the general term in general term used daily. It's part of the architecture. If you don't set pad token, operation like batching, padding, loss masking can fail or behave incorrectly. This EOS token, this guy here, this is called end of sequence token, and it indicates the end of a sentence or document. So Llama uses something like this, right? Typically, as a signal for the end of sentence termination. Now, assigning this to pad token, since Llama has no native pad token, this line reuses that end of sentence token as the pad token. This is common workaround in Llama-based fine-tuning setups. So it's safe because the pad tokens are usually masked out during the attention. It's a part of the architecture of Llama capability. So the model won't learn anything bad from it. So no harm. All right. So let's load in some data set. Earlier in previous video, we did create our data set training, eval, and test. Right. So let's look at the training. This is my original data set. Right, this here is my original data set, and that's typically that is in a dataset object, and from the Hugging Face dataset library. And what this is doing is each item in it is expected to be a dictionary with at least the key instruction, input, and output. This map applies lambda, a function. Now, this function here using lambda applies this function, which I have to go up now and complete. It applies this function, okay, to each example in my data set. The output of this tokenizer function will be a dictionary when I complete it, or a dictionary like with the same or new fields. The resulting data set tokenized trained data set will have tokenized fields like input IDs, attention mask, and labels. So before we move beyond here,